Okay, welcome back, everyone. So today it's my pleasure to welcome Steve Azzolin, who will be the third speaker in this series on graph deep learning. So today we'll be talking about explainability and also do some coding there. Yeah, thank you, Steve.
Yeah, thank you very much for the introduction. Hello, everybody. My name is Steve Azzolin, and today is the third lecture of our hands-on introduction to graph deep learning series. Currently, I am an LS PhD student at FBK and University of Trento, and today's goal is to have a look at some explainability for graph neural networks, which means to try to shed at least a bit of light into the black box realm of deep learning models. Just a reminder, you can always find the previous material and also some links to the previous recordings to our GitHub repo, where we will upload also all the material, both from the theory side and also from the practical side, so the Jupyter notebooks. Today's agenda is to first motivate why we may need explainability for deep learning models. I will try to convey some ideas of what we can do with explainability, since it's a very general and broad term. And then we will dive into some examples of explainability for graph neural networks. During the talk, questions are welcome at any time. I may struggle a little bit in checking the chat along the way, so feel free to unmute yourself and speak loudly. They are more than welcome. So let's start. Well, we all know probably that deep learning models can achieve great performances, right, in a great variety of different tasks, sometimes even surpassing the human performances. And for this reason, deep learning models and machine learning models in general are being adopted more and more also in high-stakes applications, such as surveillance, crime rate predictions, medical diagnosis, and autonomous driving. And I'm sure that you can find some other examples that are not listed here. However, there are a bunch of problems with deep learning models, well-known problems that may actually affect the way that people perceive those technologies. For example, let's consider this shortcoming. In this paper, dating back from 2019, the authors showed that by training a convolutional neural network on this dataset, the Pascal VOC dataset, you get actually a model which is not really behaving as expected, in the sense that even though the model is correctly predicting the presence of the horse in the image, if you use some explainability technique that we will see later, you can actually see that the model is mainly focusing on a specific, on a very strange watermark on the bottom left of the image. At this point, if you try to remove the watermark, so in the scenario on the bottom of the figure, you get that your model is no more predicting the right label. So at this point, you may question, like, did the model really learn what a horse look like? And in this case, it seems not. The prediction of the model is indeed just relying on the presence of the watermark, which may be present, for example, in every image containing a horse, maybe for the way that images were collected, or because a certain photographer likes to put its own information into the picture. And this can happen at any time around it. And so at this point, I'd like to make a bit of provocative question, maybe. So let's consider a system where you have to predict the presence of certain diseases, starting from, for example, X-ray images. Would you really trust the prediction of such model, knowing that they may fall into this kind of shortcomings? Well, probably the answer is not really. I mean, personally, I would feel more comfortable knowing that there is some kind of maybe human feedback, or maybe that the system can provide the rationale of its prediction, right? So in order to make sure that the final prediction is well motivated by the data. Let me make another example. Here we have a detection system which, taking an input image, it tries to predict everything it sees in the image. And in the first case, it correctly predicts the presence of the cow, the pasture, the grass, no person, and the mammal with high confidence, and everything works well. Now, if we change a little bit the scenario, we see that the predictions are no more very well aligned with our expectations, in the sense that It is predicting the absence of a person, water, beach outdoors, and seashore. But there is no really prediction from the cow, even though it's pretty clear from the image that it's right there, right? I mean, it's not hidden in a certain tiny point of the image. It's pretty in front of our eyes, but the model didn't manage to see it. Another example, the third one, present the two main errors. For example, it is predicting the absence of people, so no person, while actually in the background there are a bunch of them. It's predicting the presence of a mammal, water, beach, and two. So again, even though the mammal can be quite related to the cow, it's not really predicting cow. So again, it didn't manage to see it. And at this point, we may wonder, why is it the case? And let me try to clarify this a little bit via the following, let's say, intuitive structural causal model here. I'm not trying to be formal on the causal inference side. I'm just trying to convey the intuition behind it. So let's assume these two generative factors underline our data generating process. We have the presence of the cow and the grass, let's say. And they both influence the final image that then we have as a realization, basically, of the two generative factors. And I think that we all agree that the final label, cow, is just by the presence of the cow in an image, and it's not causally related to the grass in a certain image. Consider then the correlation between the presence of the cow and the grass, because in our real world, I think that we all agree that there is a level of correlation between a picture depicting a cow and a green background, right? I mean, I do like thinking to cows as being free in the pasture below the mountains. And that's pretty much what you probably find if you search on Google Images. Then you can always, of course, find cows on farmer house, etc. But I think that we can all agree that there is a degree of correlation between the two. And this degree of correlation is actually the correlation that will be modeled by the machine learning model, which does not have access to the individual generative factors, but it can only see the final realization, which is the image, which contains both of these two information entangled together. And the machine learning model by itself is not able to disentangle the two. And so in the end, it will end up learning the correlation between the two, and thus predicting the label cow also from the grass. That's why then in the previous example, if you don't have the grass in the background anymore, but you have something that the model has never seen during training, such as a beach or the seashore, then the model can no more predict the label cow. And this is obviously an issue, right? And so instead, the models tend to pick up these subtle or shortcut features that are correlated to the target label, but not really causally associated to it. I would like now to move to the first brief code session, in which I will try to make such an example with a toy dataset that is described by this simple structural causal model. In order to really see with our eyes and with our hands-on experience, what does it mean to learn the wrong causal associations? In this simple example that we will see in a bit, we have three random variables, x1, x2, and x3, which are sampled from a normal distribution with some parameterized mean and standard deviation. Then we have our target label for our binary classification task, which only depends on x1, but it exhibits some correlation with x2, in the sense that y is somehow influencing x2, but not vice versa. And the variable x2 is also influenced by an external, let's say, environment variable. I think that we can now switch to the code to have a look at what does it mean in practical side. So here again, we have a summary of our underlying model. First, we import some libraries like NumPy and the very handy library for machine learning models, scikit-learn. And in this specific case, we will have a look at logistic regression model, which is a very simple model, and a more complex one, a multi-layer perceptron. To start, we can first define the way we create our data, which follows the structural causal model defined above. So we have variable x1, x2, and x3, which are sampled from a Gaussian distribution with a parameterized mean and standard deviation. And in particular, x2 is exhibiting the specific causal association with variable y. However, you can see that variable y depends only on x1 and not at all on x2. And then obviously we create a number of samples in order to run up some statistics, let's say, and we do some post-processing operations in order to put the data in a format that can be consumed by the scikit-learning library. Once we have defined this function,
can I ask a question?
Yeah, sure, please.
Can I ask a question, please?
Yeah, sure. Go ahead, please.
The way you define y, it means like y is taking, it means like y is taking the value from x1, but only the value that are greater than or equal to mu1, right?
No, in the sense that it is telling a Boolean value.
Is a Boolean.
Yeah, it's a Boolean value.
I think it's a Boolean type, right?
Yeah, it's a Boolean value.
Okay.
So it's either 1 or 0. So it's a binary classification task. Okay, thank you for your question. At this point, we want to create some data, specifically from 3 different environments, depending on the environment variable. So since x1 and x3 are not influenced by this additional variable, their statistics will remain constant across environments. The only thing that will change is the standard deviation of x2, and this is implemented by simply calling the previous function by keeping constant the mean of x1 and x3, and by changing the standard deviation via different orders of magnitude. And we invoke our function for the 3 environments, and then we can collect all the data in a handy data structure, which is a Python dictionary, so that we can then access to the data for the 3 different environments via simple dictionary lookup. And we will be working with a small data set made of 1,000 samples and 3 features, so x1, x2, and f3. And the variant variable is just a single Boolean array of 1,000 samples, one for each row in our X table, let's say. So now what we want to do is to fit a fairly simple machine learning model, in this case, a logistic regression, we train it on the first environment and we check how it performs also on the other environments. And we can do that by simply instantiating the logistic regression function from the scikit-learning library and fitting it on the data from environment 1. Since the task is pretty easy, even a simple logistic regression can solve the task, and we can get an accuracy of 1 by calling the score function provided by scikit-learn. So until now, let's say that everything works as expected. At this point, the question is, does this generalize to the other environments? So let's verify and let's compute the accuracy or the score function also on environment 2 and 3. And what we get is that the performances steadily go down.
And I wanted to ask a question about the score functions.
Yeah.
Usually the score function, we know, like it's a way of associating like vectors or numbers to a node or a graph. But here now, how are you associating? Or maybe is it just a function in the PyTorch or scikit library? How is it going to work? Or because we know that there is also a lot of type of score function. I don't know.
Yeah. Okay. Yeah. Thank you. Well, in this case, the score function is simply, let's say, a shortcut for providing the final accuracy of your model. So it takes as an input 2 arguments. The first one is the data on which you want to evaluate your model. And so for this data, it will do the inference with your model, in this case with your classifier. So it will make the final prediction right. And then it takes also the ground truth related to the input sample that you gave in the first parameter, and it checks the accuracy between the two, between the y hat, which are your predictions, and the y ground truth. And it does this in a single function. So it's like, instead of coding this yourself, as probably we did last time with PyTorch Geometric, in this case, scikit-learn provides a single function for doing so in a very convenient manner. So it's just really, let's say, a convenient way for computing the accuracy.
Okay, thank you. Thank you.
Thanks to you. Okay, so yeah, I mean, it can be a bit unexpected, right? On environment 2 and on environment 3, the performances steadily went down, even though our target variable y is influenced only by x1. So at this point, one may ask, okay, but what did the model learn? Can we somehow inspect what it is learned? So can we judge the goodness of the model regardless, let's say, of the final accuracy? Because the final accuracy, we saw that can be a bit misleading if evaluated on the wrong environment. And for this simple logistic regression, it turns out that it is possible to inspect, let's say, the underlying working of the algorithm. I want to recall you how the logistic regression is defined. It's a simple sigmoid function applied on a weighted combination of the input features. So in the end, what the model will learn are just these three parameters associated to the three input features, W1, W2, and W3. And so what we can do is to inspect those individual weights, and we can do that via the coefficient parameters that is provided by the scikit-learn library to really plot or to show better these three parameters. So what we get is that the parameter W1 gets a value of roughly 3.5, W2 of roughly 5.6, and W3 is almost 0. As you can see, the fitting of the logistic regression ended up in giving more importance, so a higher value in terms of weight to x2, which, if I go back to the structural causal model, is not really the right reason or the right way for predicting y, right? Because in principle, you will give a value of 0 importance to x2 and x3, and the maximum value to x1 in order to predict y, since the causal association here is unidirectional. However, the model assigns an high value to x2, and so since x2 is changing, it's varying across environments, you will end up with very skewed predictions. And so in this way, you can somehow judge the goodness of what the model has learned from really a point of view from inside the model, let's say. And at this point, I would like to do the exact same with now a deep learning model. So a more complex one, a multi-layer perceptron, in this case with just 2 layers and with 100 hidden units. And we can do the same very conveniently with the scikit-learn library. So we train a simple MLP classifier for 700 epochs over the data coming from environment 1. And then we call the score function over the 3 environments. And again, we get this drop of accuracy. So we can do, again, the trick of before to inspect what the model has learned in order to understand why it's performing so poorly. And also for the MLP case, we can inspect the coefficients parameter of the library. However, in this case, it turns out that the number of parameters only in the first layer is correspond to a matrix of 3 by 1000, which correspond to, you know, this big matrix of number, which now is difficult, I would say, to interpret right. So in the previous case, I was showing you 3 numbers, and out of these 3 numbers, you could say, look, the model is giving too much importance to the wrong feature. So the model, like, you cannot really trust the model across different environments. However, in this case, it's much more difficult, if not impossible, to understand the relevance that is associated to each individual feature. So if that is clear, I will go back to the slide. To tell you that indeed not all machine learning models are created equal. We can identify, let's say, two main families from an explainability point of view: the white box models and the black box models. The white box ones are, for example, linear models like the logistic regression that we saw in the notebook, which is a pretty simple model and it's fairly interpretable, as we saw, and also decision trees. For people not very familiar with decision trees, it's a very basic machine learning model which builds a tree of decisions, as the name suggests, and for every node, the algorithms pick a feature to split on. It learns a certain threshold to split on, and so you start from the bottom of the tree, and for every node, you check whether the value of your sample is greater or lower than the specific threshold for the feature associated to the node, and you either go to the left branch or to the right branch. You continue like this until you reach a final leaf which contains the final prediction. In the way that the model is structured, you can see that if you check the decision patterns, the decision rules, is quite understandable by a human. And so in general, white box models are the ones that can be more easily understood by, let's say, practitioners. In general, however, they are shallow models. They tend to be good for tabular data, and they tend to be good also with few data. On the other side, we have instead the black box models, which correspond to the famous models that you may read on the web right now, like transformers, which are the base of ChatGPT, or convolutional neural networks, or the topic of our series, or which are graph neural networks. This family of models tend to be deep, if not very deep, and they're especially good for structural and high-dimensional data, and they typically shine with big data. So you can really see that they complement somehow each other. However, I would like to make a small caveat about white box models, in the sense that being simple does not necessarily always imply being understandable by humans, because in the previous example of our simple logistic regression, if we had like 1,000 features, then we would still struggle in understanding 1,000 parameters, right? And the same for decision tree. So if I give you this decision tree and I ask you to explain me a certain prediction, you will have harsh times, right, in navigating yourself across this maze. So being simple is not a panacea, or it's not like bulletproof, I would say. At this point, it may seem pretty much clear that there are two possible directions we can go as a field. We may either need to develop external tools that can inspect the model and give the rationale behind the model's prediction, or we may need to develop new algorithms that are equipped by design with better interpretability. An example of this direction are concept bottleneck models, which are often referred to as gray box models, in the sense that they settle a bit in the middle between white box and the black box. Since the focus of this talk is mainly in explaining already trained models, or in providing rationales to deep learning models, we will only focus on the first branch. But in case you are interested, I leave you a reference to a paper that talks about this new, let's say, branch of gray box models. So for now, let's proceed with the first branch, with the first point. As I said, we are interested in developing tools for explaining deep models, right? However, explainability as a keyword is a very broad term, and it can be used in different use cases. So before diving deep into how to use these tools for debugging the models, I would like to spend 2 slides in providing to you a very brief overview of other 2 use cases of explainability, really just to give you a glimpse of what's going on in this field, starting from hybrid decision making, which is a very trending topic right now, I would say, and this is testified by the fact that just a few months ago there was the first workshop on hybrid human machine learning and decision making at SML PDE conference in Turin, and also very recently the first international conference on hybrid human artificial intelligence was created with the aim of developing new algorithms that can cope better with the human. So not only, so let's say inserting the human into the deep learning loop in order to give some trustworthiness in the overall process. Talking about people working on it, it's quite recent, the creation of the Hybrid Intelligence Center in the Netherlands and the Tango project funded by the European Union and which includes a great variety of different partners across Europe. So yeah, this was a very brief overview of like one direction of explainability. So empowering the human with AI capabilities and empowering AI with the trustworthiness of the human. Another possible use case is algorithmic recurse, which can be formally defined as the systematic process of reversing unfavorable decisions by algorithms across a range of counterfactual scenarios. So let's consider very briefly this example in which there is a decision maker which has to take a certain decision based on a black box model. You then give like your data, probably your personal data, and then, for example, the bank then refuses your loan request, and maybe you get mad because they didn't really provide an explanation, since black box models are not explainable by themselves. And in this case, algorithmic recurse aims at providing back to the user a sort of goal profile or like some set of minor modifications that you can apply to your profile in order to push the model to provide a different outcome. So in this case, to actually give to you the loan. Okay, I will stop here. Let's say different use cases because now I would like to focus on our main focus, which is the model debugging or inspecting what's going on inside the model. And for doing so, in the past few years, a bunch of methods have been proposed to try to do that. For example, Shapley values, Lime, and integrated gradients. For image-like data, those algorithms tend to give, as an explanation, typically either a heat map or a series of relevance regions. So this is the, on the left, you probably recognize it, is the picture from the first slide. And here, an explainability algorithm indeed can give you as a heat map the region where the model is focusing, which in this case is indeed the watermark. But they can highlight also like correct regions. So if you are predicting the motorbike, then in the bottom example here, the model is actually focusing on the right region. And on the right, we have another example of possible shortcoming of models in which an husky is classified as a wolf just due to the snowy background. Since in this data set, the vast majority, if not all wolves in the data set are annotated just in front of like some snow or a white background. And so in this case, when the model predicts wolf, it is just looking at the presence of the snow without really looking at the main subject of the picture. And you can debug the model via this kind of explainability tools. However, so far we have been talking about image-like data, right? Just to give you some context. However, the graph domain poses unique challenges. For example, it's an unstructured data type. It's an intrinsically discrete object. It comes with attributes or features on nodes, edges, or on the graph itself, and it's not always easy to deal with all these distributed information. And also the explanation by itself comes in a different format. And so it's pretty clear that we need to develop novel techniques for dealing with graphs and graph neural networks. Before going on, let me clarify in the same way that I did for images, what does an explanation look like for a graph? So hope that is pretty clear that for images, heat maps are a good choice to go with. while instead of for graphs, we can opt for two main families of attribution methods. Node attribution or edge attribution, that, as the name suggests, either gives the some importance score or relevance score to the individual nodes of a graph or to the individual edges. And in this specific case, darker colors means higher importance. So for the node attribution example, in this specific case, the explainability tool that was used in order to generate this image is correctly in assigning higher scores to the nodes belonging to the grid. While for the edge attribution, the algorithm is again giving pretty high attribution scores to the edges of the grid. However, here probably it's not working like perfectly because it's giving also much higher importances to some spurious edges. However, the two representations are pretty much equivalent. So you can go from a node attribution to an edge attribution by, for example, doing the average of the nodes incident to a certain edge. The only difference is from an operational point of view. So depending on how the algorithm is implemented. Some of them are node level and some are edge level. Talking about the tools that have been developed so far, we can have a look at this nice taxonomy proposed by Wan et al. Who identified the two main branches: instance level explanations on the left side and model level explanations on the right side. So in the next slides, we will have a look at the main differences between the two branches, and we will also have a look at some code implementing an instance level explainer. So I will say that we can start from the instance level or local explainers. It's two frequently used terms. In general, the main characteristics of local explainers is that they highlight the input features that are most relevant for the prediction of the model that you want to explain. And here, I would like to highlight the fact that they give you an explanation for every sample. So in this picture, we have two samples, sample 1 and sample 2, which are taken from a certain data set, which contains graphs with this grid-like structure. And we can see for, I guess, 9 different explainers, an example of an explanation. Some of them, the orange one, provide an explanation in terms of the node, while the green one in terms of edges. And you can see that more or less pretty much all of them tend to agree to give high scores to nodes or edges belonging to the grid. But then, of course, there are some outliers like this PGM explainer, which didn't really work well. It was assigning just a very high score to one single node, which, by the way, didn't belong to the grid. And also, integrating gradients edge for sample 1 didn't manage to give higher importance to the grid. So we will talk later about how to evaluate explainability. Here is just to give you a brief overview of the different behaviors of different explainers. And now I would like to focus specifically on two of them, namely GNN explainer and PG explainer. Starting from the first one, GNN explainer, is the first actually algorithm that was proposed to try to explain the decision process of a graph neural network. And intuitively, the problem for the algorithm is formalized as follows. So if you have, if a certain edge is relevant, it means that removing it will decrease the confidence of the prediction, right? It makes sense. However, given what I said at point 1, if you want to find the explanation, GOS, you will seek for the edges whose removal do not impact the prediction of the model and remove them in order to get a sparse graph as an explanation, which, however, contains the information necessary for making the correct prediction. And this mathematically can be formalized as maximizing the mutual information between the target Y, so your label, and the explanation that is being maximized. If you do some simplification, you can actually get that this boils down to minimizing the conditional entropy of your explanation that you are interested in. And note that here you will typically add also some regularization terms in order to induce the sparsity of the explanation. So to get as an explanation the few edges possible, which make the explanation more human understandable. And operationally, the explanation is then found by optimizing a mask at edge level, since GNN explainer is an edge level explainer over the graph. And you can get something like that, which is the same picture as before. So you will get an importance score for every edge in the graph. At this point, I would like to spend a few words also on the other explainer, PG explainer, which is closely related to GNN explainer, since it shares the same principle as the previous one. Yeah, in this case, however, instead of optimizing a mask for each input graph that you want to explain, it instead trains a neural network that takes as input the features of a certain edge and predicts straight away its importance score. And the pipeline can be conveniently summarized as follows. So you have the features of your input nodes, and you create the features of your edges by simply concatenating the node features incident of a specific edge. And then you forward this embedding to a multi-layer perceptron, which then spits out a series of latent variables, which are then used to sample from a binary concurrency distribution, which is nothing but a differentiable approximation of a Bernoulli sampling, which give you then the final explanation, which is used to evaluate the objective function that we saw before, so the minimization of the entropy. So to summarize the main differences between the two algorithms, while GNN explainer trains an edge mask for each graph, PG explainer trains an MLP once over all training graphs, and then at inference time it simply does inference with the learned multi-layer perceptron for each explanation. Before going to the code, let's spend a few words in how we can evaluate this explainability. In the cases in which some ground truth is available, for example, in controlled scenarios or synthetic benchmarks, for example, where you have control of the data generating process, you can simply compute the accuracy or the F1 score of your explainer. So on the about the example on the right, it's a synthetic graph where we know that the ground truth is this cycle here on the top, and so by running GNN explainer as described before, you get an explanation like that, which corresponds to the dark red edges. Well, for this specific case, you would have a recall value of 1, since the explainer managed to identify every edge belonging to your ground truth, while, however, the precision is not that high, since it spotted some like spurious edges here and there. In other cases, instead, in which you don't really have a ground truth available, you can still rely to some metrics, for example, to some unsupervised metrics, such as the sparsity, which you, in principle, would like to maximize so to obtain a small explanation as possible. Then we have the fidelity plus and the fidelity minus, which respectively you should aim to maximize and minimize. Since the fidelity plus is computed as follows. So you compute the difference between the confidence in predicting the label over your entire graph, G of I, and you subtract from this confidence score the confidence score of the prediction via removing from the graph the explanation. So in principle, if the explanation contains the relevant information, this complement of the explanation should convey no information about the final label. And so this F of the complement should be very low. Thus, the difference should be, let's say, pretty high, 10 approaching 1, hopefully, in the best case. While the fidelity minus is the symmetric case. So instead of subtracting from the original prediction the confidence of the complement of the explanation, you compute the confidence of the explanation by itself. So since the explanation, if a good explanation, if the explanation is good, it means that it is conveying the information about the target label, and so predicting and doing inference via the model on this explanation should convey the same information as doing inference over the entire graphs, and thus the difference should approach 0.
So I have a question.
Yeah, sure.
Would the explanation be like a smaller graph that kind of captures the behavior of the larger one in some way?
That's what you hope to get. Yeah.
Okay.
Of course, this is not. Yeah, sorry. You have
Yeah, no, I was
follow-up?
saying, okay, yeah.
Okay. That's good. So in case there are no more questions, I will go to the second code session. Okay. I see that there are some questions on the chat. I see Itamar not hearing the speaker. I hope that now everything is okay. But since I got some questions, I assume that you are listening me. Okay. Let me go to the beginning. Okay, so let's have a look in how to implement a very simple example of explainability tool. Here, the first part will be of this notebook will be devoted to implementing a graph neural network, because if we want to explainability, we need a model that we want to explain. And so the first part is pretty much what Antonio presented the last time. So we import a bunch of libraries that will be needed for our purpose. We define a simple graph neural network, which in this case is made of GNN layers, which were presented the last time by Antonio. And since the task that we will be working with is a graph classification task, we at the end of the forward process, a final sum global pooling to collapse the node representation into a single graph level representation, and then we classify the final representation via multi-layer perceptron. So nothing new, since it's something that we saw last time, but in case you have some questions or some curiosity, feel free to ask. The dataset we will be working with is the BA2 motif dataset, which contains 1000 graphs, which looks something like this. So this is an example of graph belonging to label 1, which is a random Barabasi Albert with an house like, it's like should look like an house. Samples. Okay, here I have another example of class 1, while class 0 is characterized by a random Barabasi Albert. So you sample a new random graph for every sample, and instead of attaching this house-like motif, you attach a simple cycle, so without this additional chord. Then to train the model, we of course need a train function and a test function. And for this simple data set, 50 epochs are enough in order to get a final accuracy of 1, or like a 0.99. So, okay, no problem. And so, yeah, this is something that we have seen. So I will move straight to the local explainer. I was a bit fast, but yeah, again, feel free to unmute yourself. For this part, we will be having a look at the PyG implementation of GNN explainer. However, keep in mind that there are also other implementation available. For example, the Deep Graph Learning Library, or the GraphXI and the DIG library, which, by the way, in my opinion, implement a more diverse set of explainers, while the PyG implementation ones is a bit limited in this sense. So if you are interested, you can check out also these additional libraries. And then there is always the original implementation of the author of the GNN explained paper, which is always worth to check. Now we can have a look at a very handy function for plotting the final graph. And in order to plot the explanation, we would like to give darker colors, let's say, to more important edges. And we can do this by defining a color variables, which takes the values as defined by the edge mask, which will be computed by the explainer, and then by feeding the network X function for drawing networks these additional options, which contains the different colors, the color map, so we work with shadows of red, and then some additional information like the node size, the width of the edge, or the node color, which is a gray-like. Yeah, it's kind of gray. Going into the main parts, implementing the explainability side, PyG comes equipped with a handy function, handy class actually, called explainer, which lets you to define the model that you want to explain. So in this case, it will be the GNNs that we defined above. You can define your the explainer algorithm that you want to use. In this case, is GNN explainer, which is trained for 200 epochs for every graph. And then you have to specify a bunch of other parameters which are pretty standard in the implementation of PyG. Exception done for this task level parameter, which might be worth spending a couple of words on, since it's controlling whether you are working with a graph classification task or a node classification task. So in case you want to check out a node classification task, you should change this task level from graph to node. And in case you are interested in checking out the PG explainer, you have simply to replace PG explainer in the definition of the algorithm here. And then you have to train the underlying the PG explainer, since it's like the main difference between PG explainer and GNN explainer. And you can achieve this via the 5 lines of code that I reported here for convenience. In this case, I will be working with the GNN explainer as a baseline. And in order to, like, once we have defined this explainer class, GNN explainer is ready to be used. And so what we do is to simply call the forward function in this way. So doing like calling the explainer on a specific instance. In this case, we are selecting the graph number 2 from our dataset, and here we have to pass separately the node features, the topology information, so the edge index, and some other information. Here, an important bit is that for graph level tasks, we have also to specify the batch, which tells basically the underlying graph neural networks how to aggregate the node level information. And this must be done in the following way, which basically will take the batch and will forward the batch straight to the forward function of the graph neural network. But this is an implementational consideration. For node level tasks, you don't need this line of code. At this point, once we have called the forward function of GNN explainer, we can get the explanation subgraph, which now gives us the edge mask, which now represents the importance for each edge. And before plotting, we aim at doing some very simple post-processing operations, for example, to normalize the scores in a 0-1 range, and also to set to 0 the values that are below a certain threshold, which is specified, let's say, by the user. So in this way, our final plot will contain only the most relevant part, completely hiding the less relevant one. And then this network X function simply converts this edge mask into an actual network X object, which can be plotted with the function that we defined above. And in this specific case, we want to first plot the original graph and then the explanation in order to check the differences between the two. And the original graph, which is a graph of class 0, indeed you can see that the additional motifs does not have the additional chord, so it's a simple cycle, and it looks like that. While the explanation that was computed by GNN explainer looks like something that we saw before. So it is highlighting the cycle as we were expecting. And in this case, it is highlighting also some other spurious edges, which the explainer considered to be important, but that are not really in our graph field. Okay, so now we successfully extracted an explanation, and we can try to compute the metrics that we discussed above. Specifically, we will be implementing the fidelity plus and the fidelity minus. To compute the fidelity, I defined this easy function, which simply takes either the edge mask or the node mask, depending on the on what your explainer is giving to you, and first makes the prediction over your input graph. So it is computing if you let me go back to the slide, it's computing this f of g. And then you want to compute the f of the explanation, and then the f of the complement of the explanation. And then you simply implement the formula. So you do the original prediction minus the complement for the fidelity plus, while for the fidelity minus, the original prediction minus the prediction made just on the explanation. And so we can simply compute the fidelity of our explainer over the explanation that we defined above, and the results are something like that. It's a value of 0 for the fidelity plus and a value of 0.14 for the fidelity minus. Here again, I had to set an additional attribute to the explanation in order to compute correctly the fidelity, and this is due to the fact that in my opinion, the default implementation of PyG does not cope really well, at least for what I've seen with the graph classification tasks. And so you have to cope a little bit with these additional batch parameters here and there. And so again, this is needed if you want to evaluate a graph classification task, but not really for node level tasks. We can implement also the sparsity metric, which is much easier in this case. You first compute the number of edges of your input graph, which comes pretty handy from your input.num edges. It's a value pre-computed by PyG. While for the number of edges of your explanation, you can simply do the sum of the importance scores that are above your threshold. So you have to decide a certain threshold, and then everything that is above it is considered as important, and you simply compute the ratio between the two, or better, 1 minus the ratio, so that higher values of sparsity are actually to be, let's say, are the ones to be ideal. And in this case, since the explanation was pretty small, right, it was a simple cycle plus 2 or 3 spurious edges, the value is pretty high, meaning that we were able to prune the majority of irrelevant edges. For this side is all, so I will go back to the main slides, unless you have any specific questions. Okay. So let me briefly go back to the main taxonomy. We presented just a couple of examples of perturbation-based distance level explainer. So hope you can see my cursor, but we are in the leaf here of the taxonomy, and we saw GNN explainer and PG explainer. But as you can see, there are a bunch of other approaches out there, which for the sake of time, of course, I cannot describe all of them. However, I'd like to give you a couple of pointers to recent surveys in the literature, which present more or less the main ideas, the main state of the art, and also the main limitations of what I've presented so far. And talking about limitations, I would like to present a bunch of limitations by myself to motivate the need of more research in this field. because experimental surveys too often report that random baselines in some specific cases surpass explainability tools, which is obviously not ideal, I would say. In a recent survey, we also highlighted the non-robustness of many explainability tools, meaning that an explainability tool, so an algorithm that works well in a certain setting, does not work well anymore on some other specific settings. Then there is an issue with out-of-distribution samples during the perturbations, because, for example, when you complete the explanation, you try to remove edges, right, which should be less relevant. However, in doing so, you may create very strange graphs which are not present in your training data, and so that your model is not very used in seeing, and which correspond to out-of-distribution samples. And then a personal take that it is often the case that the focus on the final metrics, so improving the state of the art, is maybe too often the final objective of these algorithms, rather than checking whether the explanation actually helped the human or the debugging of the model, since the metrics are not super aligned with, let's say, the human interpretation. So, okay, after this, let's say, brief overview of the limitations of local explainers, I will very briefly describe a little bit the other branch of the taxonomy, just to give you an overall idea of the current state of the art. So let's talk about the model level explainers, or also referred to as global explainers. Contrary to local explainer, global explainer, as the name may suggest, tries to capture the behavior of the model that you want to explain as a whole, trying to abstract the individual noisy local explanations. So we saw that local explanations for big data sets can be simply too many to be manually inspected, because you have one or more explanation for every input sample. They're often noisy, and as we mentioned 2 slides ago, their quality is often difficult to be evaluated. And so it makes sense, right, to provide a new perspective into aggregating those local explanations into a more abstract representation. And this is exactly what we try to do with GLG explainer, which stands for Global Logic-Based GNN Explainer, which extract logic formulas which are expressed in terms of learned human understandable concepts. And the reason for choosing logic formulas as a way to represent an explanation rather than a node mask or an edge mask, as we saw before, is that logic formulas with size constraints can be typically well understood by human experts. Let's take, for example, this use case. We have a data set made of mutagenic or non-mutagenic compounds, and you train your favorite graph neural network architecture for discriminating the two, and you get a very nice or a decent accuracy at least. Then what you can do via GLG explainers, that you can extract a bunch of logic formulas summarizing the behavior of the model as a whole, so not in terms of single explanation, but as a whole, yeah, as the name suggests. And in this specific case, for class 0, which corresponds to the class of mutagenic compounds, you get that the mutagenicity of a certain compound is typically implied by the presence of the functional group NO2, or the presence of the functional group NO2 and some other components like carbon rings. And the interesting bit here is that if you check the literature about mutagenicity, you get that this specific functional group NO2 is highly correlated with the mutagenicity of a certain molecule. And so this means that the model learns to recognize this specific functional group, and this logic explanation is telling you, look, that the mutagenicity is typically implied by this presence, by the presence of this functional group. And so this gives really a way to the human expert to evaluate whether the model correctly learns the underlying pattern in the input data. While instead of the class 0, so the non-mutagenicity is implied by, let's say, everything else, so carbon rings, etc. The important bit is that there is no functional group NO2 in the non-mutagenic class. Just to give you a brief idea of how GLG explainer works, it first extracts a bunch of local explanation with your favorite local explainer. So, for example, one of the algorithms that we saw in the left branch of the taxonomy, and then you feed those local explanations to GLG explainer, which is now trained with the prediction of the model that you want to explain in order to spit out the final logic formulas. So from an abstract perspective, GLG explainer is learning how to combine the individual local explanations provided by a local explainer into a single logic-based formula. And before closing this presentation, I'd like to give another example of how these logic formulas can give insights and can help you in debugging your model. This example is based on this toy dataset. It's called the multi-shapes dataset, which is composed by random Barabasi-Albert graphs, which are sampled for independently for every sample that you want to add to the dataset. And then the graphs of class 0 are attached to one of those motifs that are depicted here. So you can either attach an house or a grid or a wheel or a triplet of the three. While instead for class 1, you again concatenate or you attach to a random Barabasi-Albert graph the three possible combinations of the two motifs. And so on the right, you can see a couple of examples of graphs belonging to class 1, since they exhibit at least two atomic motifs. In this case, a grid and an house, and in this other case, the grid and the wheel. A detail worth of notice here is that the samples having this specific triplet are very few and are only present in the train and in the validation split. So at this point, what we have to do is to train a graph neural network in discriminating class 0 and class 1. This task is pretty easy, and so even a simple GNN can solve with a decent performance the task. However, note that the train and test performance are misaligned. And if you inspect what's going on, basically you see that the model did not learn to model this specific triplet of class 0. And the difference between the accuracy is indeed because in the test set there are no triplets, and so the GNN is predicting everything perfectly, while the train and the validation split do contain the triplet, which is not modeled by the graph, and so the accuracy gets lower. At this point, we want to run and check what GLG explainer spits out, and we can see that the final formulas are pretty much aligned with the ground truth here on the left. So for class 0, we have the Barabasi, only the Barabasi, or the presence of the grid, or the presence of the house, or the presence of the wheel, or the presence of the Barabasi and the house. And look at that, this is a bit redundant, so it's like an imperfection of the final formulas because it's redundant. For class 1, again, it contains the three different tuples of the atomic motifs, but it contains also this specific triplet, which in the ground truth belongs to class 0. However, since the explainer is trying to really tell you what the model has learned, it is put in this triplet in class 1, meaning that for samples that do have all the three atomic motifs, then class 1 is triggered in the model. And so in this way, you can really tell, okay, my model learned to assign the triplet to class 1. And so, I mean, you can give a sort of judgment about the model, right? Because if you have the knowledge about the ground truth, you can say that the model did not learn the correct pattern. And in this way, you can spot this issue. Of course, also, this approach is not bulletproof in the sense that the number of concepts that appear in the logic formulas must be defined a priori. And it is based on quite strong assumptions that the underlying local explanations should be good. And so it assumes a nicely working local explainer. I would like to give some conclusions. So to recap a little bit what we have seen so far, and then I will be happy to take your questions. So we have seen the common shortcomings of standard deep learning models. I try to convince you about the premises and the potentials of explainability as a whole and consider in general terms. And then we saw some example with some code of explainability tools for the graph domain. And also we discussed briefly the limitation of the current explainability tools. So this presentation is over. Let me give you a very brief hint of the next session, which will be also the last one of our series. And we'll be talking about heterogeneity in a graph neural network, which means how to model and how to learn to incorporate the diversity of different edges into our graph neural network. So not all edges are created equal, let's say. And yeah, thank you very much. I'm happy to take your questions now.
Yeah, thank you very much. Thank you. Any questions?
I have one doubt, that is in the previous lecture that we have attended, we have got a GitHub repository in that the tutorial of previous lecture was given, but today's lecture was not given in that tutorial. So I think if you could share it with us, it would be great. Could just try it with our hands.
Yeah, absolutely. Right after the presentation, I will upload everything on GitHub. I just waited because I made some last time modifications to the code.
So
yeah,
do we
absolutely
check the same GitHub repo for today's and for the upcoming days?
Yeah. It will be everything on the same GitHub repo.
Okay,
we will add
Thank
some
you.
additional folders.
Thank you. Yeah. Thank you. And it was a great session. Yeah.
Thank you very much.
Yeah. The representations were very appealing. Yeah.
Appreciate it. Thank you very much.
Other questions? All right, seems not. Okay, thanks again. Thank you, Steve, for the nice talk. Thank you very much.
Thank you very much, everybody. Thanks for attending, and